And okay. Now this practice exam is going to contain information from all of the exams and quizzes that we've had up in, throughout the entire course. And I intend to give you some information on it. And um, I'm thinking I can put that table that's at the top of the screen you're seeing now, maybe on your review quiz when you take it, so that you'll have this information to you. Now, you know R, I'm sure, and these, but this is just to help you remember the other units that we could use. Okay, now, let's look at number 1, and says, which weighs most, 12 grams of fluorine, or 0.36 moles of fluorine gas, or 3.6 times 23rd atoms of fluorine, or 2 times 10 to the 23rd molecules of fluorine. Now, if I'm looking at that, they're all different units. So what I'm going to do is I'm going to transfer everything to the same unit. And the easiest one for me to do, I think, it would be just compare everything to grams. So I know that the first one, let's see if I can narrow that down just a little so I can see it. Maybe that's big enough for me to see also. Okay. We're comparing now everything to 12 grams, 12 grams of fluorine. And that's going to be my A answer. Let's see what the other answers are in terms of grams. We got 0.360 moles. And it's fluorine gas. Now you should remember that that's F2. Fluorine, chlorine, bromine, iodine, hydrogen. Well, you know what? If you take element X off the periodic chart and boil it, what boils off is F2, or diatomic molecules. So it's kind of funny. I guess I don't understand exactly why that is, but in a sense I do. I do know that everything attracts everything else. So if you just had atoms up there, and that's all you had in the vapor, they would bump into each other every now and then. And my guess is they would become gaseous. And as they become gaseous, they'd form diatomic molecules, at least. But that's rationalization. The thing that you need to remember is the gases on the periodic chart are all diatomic except the noble gases. Helium, neon, argon, krypton, xenon, and radon are gases, but they don't. They're not diatomic. They're just monatomic. So I want to go from moles of F2 to grams of F2. And 1 mole would be 2 times the atomic weight of fluorine is 19. Essentially, that's close enough. So if I had 0.36 moles times 2 times 19, that would come out to be 13.68 grams. So far B is ahead. Now if I go to the C response, it's 3.60 times 10 to the 23rd, and it's atoms of fluorine. Well, we got to convert from atoms of fluorine to grams of fluorine. and 1 atomic weight of fluorine, 1 atom of, I'm sorry, 1, I want to do this into moles, yes, that many atoms. So if I had 6.02 times 10 to the 23rd atoms, that would be 1 mole of fluorine, which would be 19 grams. So I want 3.6 with an exponent that's 23. I want to divide that by 6.02 with an exponent of 23 and multiply it by 19. That gives me 11.3, 11.36 grams of fluorine, and still B is winning. If we do D, we got 2 times 10 to the 23rd. And what is this? This is molecules of fluorine, and a molecule of fluorine is F2. All right, so we go to this. We want to go from molecules, and Avogadro's number of them, 6.02 times 10 to the 23rd, would be 2 times 19 grams. So 2 with an exponent of 23 divided by 6.02 with an exponent of 23 times 2 times 19. I get 12.6 for E. So it's 12.6 grams. So again, it looks like B is the winner for number 1. Okay, let's look at number 2. Now, the whole point of this first problem that we did was to use Avogadro's number, to know when to use Avogadro's number, to know what the formula of that compound is. In this case, was just atoms, and we were dealing with knowing that fluorine gas is F2. So that was sort of the key to that problem. Now we're going to look at a reaction for the next 2 questions, and it has to do the reaction of 1.2 times 10 negative 1 moles of chlorine would produce what mass of PCl3? And so our reaction for number 2.
Dr. Pearson?
Yes.
I know you just said that you multiplied it by 2 when it was a gas, but do you mind explaining that a little bit more?
Okay. Whenever you're dealing with the gaseous elements off the periodic chart, they are hydrogen, oxygen, nitrogen, fluorine, and chlorine. All of those are diatomic gases. The other elements that can become gaseous rather easily are bromine. It's a liquid at room temperature, but it does have a vapor pressure. So that vapor over the liquid ammonia, liquid bromine, would also be diatomic. The same thing is true with iodine. Iodine, you've really probably never seen iodine. You think you have. You've got it in the drugstore. You put it on cuts. Well, what you put on a cut is iodine, I2, dissolved in potassium iodide. So in potassium iodide reacts with the I2 to make the I3 minus ion. So what you see as the brown color in iodine, like you put on a cut, is that particular triiodide ion, and it's brown. Iodine itself is a purple solid, and In fact, it's got so much vapor pressure that you can see a purple color in the gas over it. And um, it does the same kind of process that carbon dioxide does. Solid carbon dioxide, dry ice goes directly from solid to liquid, to gas. That's sublimation. Iodine sublimes as well. And iodine, when it vaporizes, is I2. So as far as we're concerned, the gases of hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine would all be diatomic. And noble gases, helium, neon, argon, krypton, xenon, and radon, do not form dimers because they don't form compounds very easily. So the only ones you have to remember in dealing with the elemental gases would be the ones I just mentioned: hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. Okay, is that good?
Yes, thank you.
Okay. Okay, let's look at number 2. The reaction we've got is P4 reacting, and it's gaseous in this reaction. That may be important. Plus 6Cl2, and in this one, that one wouldn't ordinarily be gaseous. P4 is normally a solid at room temperature, but again, you can heat it up very easily, and it makes the P4 vapor. Phosphorus is tetraatomic, both in the solid and the liquid and the vapor. It's P4 molecules. In the solid state, it can take 2 different three-dimensional arrangements. One of them is yellow and one of them is white. Yellow phosphorus is stable to air. White phosphorus will catch on fire in air. And it's really the same stuff. It's just the way the crystal structures are different. And you can do a neat little demonstration of spontaneous combustion by taking a little bit of white phosphorus, and it dissolves in several different solvents, but there's one called thionyl chloride that dissolves it very well and is pretty volatile. And you can dissolve a little bit of white phosphorus in that, and then you can put it on a piece of cotton or something like that. Just put a little bit of it, maybe soak the cotton with that. And when the cotton dries the thionyl chloride away, it'll catch on fire. It's kind of a neat little magic trick. I used to do a magic show, and I had so much fun with that. PCl3 gas. Okay, so here's our reaction that we're looking at, and it says if I want to react 1.23 times 10 negative 1 moles of phosphorus, so that would be 0.123 moles of phosphorus, and 476.5 grams, 476.5 grams of that. We want to know what mass. I want to know how many grams of PCl3 would I get. Okay. Since this is in moles, the equation is showing 1 mole, so I don't have to do any calculations there. But this is in grams, and the equation is showing 6 moles. Each mole has 2 chlorine atoms, and the atomic weight of chlorine is 35.45. And that'll be in grams then. And then this compound, we want grams, so I need 4 moles. And each mole will have 1 phosphorus, 30.97, I think. Yep, that's it. 30.97 plus 3 chlorines, and that's 35.45. Okay, all right. Now we got our data. Let's go ahead now and do the math. So of course I've got a rebalancing factor, and the first one's pretty easy. It's 0.123 divided by 1. So it's 0.123 is the rebalancing factor for the phosphorus. Now I've got, for the other one, I've got 476.5. 476.5 grams of chlorine. I want to divide that by 6 and divide it by 2 and divide it by 35.45. So that will give me 1.120 and some more digits. So 1.123.120, it's close, but looks like the chlorine is going to win. So that's my rebalancing factor. So my answer is going to be the rebalancing factor that I just calculated, that one, multiplied by what I've got under my question mark is 4 times 30.97. It's supposed to be a 0, 30.97 plus 3 times 35.45. Okay, so I'm going to put it in exactly the way I've got it written there. So I'm just going to say times 4 times a left parenthesis 30.97 plus 3 times 35.45. And if this is right, which it is not, I've got a problem here.
Dr. Pearson,
Yes.
would you not use the 0.123 as the rebalancing factor as opposed to the 1.12?
Oh, thank you. Of course I would. I didn't see my 1 there. Thank you. Of course that's right. That's why I got the wrong number here. I'm surprised I didn't give this as a choice, though. It's 615 would be if you used the wrong rebalancing factor, which I did right there. Thank you so much. I didn't see my little 1 there. I was saying 0.120 and 0.123, 0.120 smaller. All right, back and punt. So it's 0.123 times 4 times left parenthesis 30.97 plus 3 times 35.45. Now, that does look a little better, although I'm still off a little bit. Let me see, 0.123 times 4 times, I did look up phosphorus, right? 30.97. Yeah, 30.974. Okay, so that's right. And phosphorus is 35.45. I'm almost certain of that. 35.453. I'll do 0.123 times. I'm close, but close is not. Close only counts in horseshoes and atom bombs, remember? No, I'm coming out with the same answer. So it's 67.56. 67.56 I've got a 68.1. Let's see what, I think the answers are given at the end of this one. Number 2. Supposed to be B. Okay. So evidently there was some round off done somewhere. Could have been I sometimes use 35.5, but there's 4 significant figures and given it, no, there's just 3.
Dr.
So-
Pearson, isn't B 11.3 though?
Yeah, it is. I was looking at A.
I did that for a second too, so I was like, I bet that's what he's looking.
Well, now let me think. Well, it wasn't. Let me be sure I got the rebalancing factor correct. 476.5. That's the amount of the yes. And there's 6 of them divided by 6 and divided by 35.45 time, and let's see. Let's do it again. 476.5. And I want to divide that by 6. I want to divide it by 2. And I want to divide it by 35.45. No, that's 1.12. Well, that key has to be wrong. Okay. I didn't notice that. I should have looked at that better. Is this the same exam that you've got on D2L? I didn't think to check that.
Yes, sir.
It is the same
Yeah.
as the practice on D2L? Okay. Sometimes I correct errors, and I usually correct them on D2L. And then I've got 4 or 5 different places where these are stored, and not all of them have been proofed enough. But if I had 1 mole, it did say 1 mole, right? Oh, I was working number 3 anyhow. Let's go back. But 0.123 is correct for up here. So 0.123 is the rebalancing factor times 4 times 30.97 plus 3 times 35.45 close. I'm still getting it. There's no way to get anything but 67.56. So just ignore those answers. I'll fix it. It's supposed to be B, it says. So I'll make that B on my copy and then fix it on D2L later. 56 grams. No, not big G, little g. Okay. Yeah, I'm going to save that. So B is the correct answer now. All right, now let's go to number 3. And what I'm going to do is just copy the stuff that's on the test for you to see. Number 3, I'm going to use, I've got P4, and I've got 6 Cl2s, and I'm going to go to 4 PCl3s. And this time it is limiting reagent. I've got 158.6 grams of this. I've got 476.5 grams of this. The equation is showing 4 times 30.97 of the phosphorus, it's showing 6 times 2 times 35.45 grams of this. And we want to know, when we're done, we want to know how much of this is present and how much of one of these is going to be left over. So to see how much of this is present, I'm going to do 4 times 30.97 plus 3 times 35.45. Okay, all right. Now we got enough there. We can get our rebalancing factors. So 158.6.
Dr. Pearson,
Yes,
can I stop you and go back to number 2?
yes.
In the product, we have four of them.
Yes.
But when you're doing the molecular weight, you only did 3 of the chloride. Shouldn't it be 12?
What I did was what I intended to do. I'll double check it. But what I intended to do was I had this 4 multiplying by that bracket.
Okay, yeah, I'm sorry.
So that would give me 12. So I've done it
You're
twice.
right.
So
Okay.
I believe I did include it. Thank you, though.
Okay.
I do
You're
appreciate you pointing out something, because I do make mistakes. That was the first one I ever made in my life, and that was the first lie I ever told, and that one was the second one, and that one was the third one. Yeah. It's like looking in a mirror. Okay, all right. 158.6, and I want to divide that by 4 and divide it by 30.97. So I'm getting a rebalancing factor for this one. I'm getting 1.280. And there are other digits here on my screen. And then for this one, I want to take 476.5, and I want to divide that by 6, divide it by 2, and divide it by 35.45. So 476.5 divided by 6, divided by 2, and divided by 35.45. Okay, that should be it. I get 1.120 and some more digits. And that's comforting, because that's when I worked it up here, I got the same answer, so I'm good. Now comparing these two, this one would be the limiting reagent rebalancing factor. So that number is on my screen now, and I want to multiply that by 4 times that parenthesis. So it's times 4 times a left parenthesis, 30.97 plus 3 times 35.45. And now close that. What I'm coming out with is 615. Yeah, I'm coming out with 615.26 grams of the PCl3. Now, how much of the P4 would be left over? So I'm going to take my rebalancing factor, 1.120122238. I want to multiply that by the phosphorus amounts, multiply it by 4 and multiply it by 30.97. And I get 138. I use 138.76 in digits. Grams of this is used. So if I subtract that number from the 158.6, that's how much P4 would be left over. So 158.6 minus that answer gives me 19.8. Okay. Oh, yes, okay. Thought it was going to ask me for the P. Well, it just says the correct answer is going to be C. It's going to have none of the chlorine in the container and 615 grams of this. It didn't give me a more, what would have been a better problem would have been 19.8 grams of P4 left over and 615, but that's not one of my choices. So the correct answer that's on the test is C. I expected that, I really expected for the excess reagent to be in there. What was I thinking? Okay, it's moving right along. Number 4, density of a gas of undetermined molecular weight is 3.014 grams per liter at 82.08 centimeters of mercury and 341 degrees. So we want to get the molecular weight of the compound. We're given the density of the gas. It's supposed to be a little rho, Greek symbol. Density of the gas is 0.860. No, that read it before you write. The density is 3.014 grams per liter. Now, it says the volume of this sample is 0.860 liters. But, you know, that's kind of a red herring. You don't need, the density of a liter or the density of a milliliter is all the same. So it doesn't matter that the sample size is that. You could use that, but, you know, I'm not going to. What I'm going to do is I'm going to say 1 liter of that gas is going to have 3.014 grams of the compound. So that's what I got from the density of the gas. So I'm going to use PV equals nRT, and I'm going to solve for the number of moles. The number of moles is going to be P times V divided by R and T. Now, what did our data tell us? It's that the pressure is, let's go sidebar over here. Pressure, we were told, is 82.08 centimeters of mercury. That would be 820.8 millimeters of mercury. And that would be 820.8 torr. Now 760 torr equals 1 atmosphere. That's going to be my conversion to get atmospheres out of that. So what I'm going to put in is 820.8 divided by 760. That's the number of atmospheres. The volume that I'm doing is for 1 liter. So that's a 1. I want to divide it by 0.0821. And now let's do my sidebar for temperature. The temperature is 341 degrees C. So I want to add 273.15 to get kelvins. So I want to divide over here by 341 plus 273.15. Okay, so I got my setup. I can do my calculation. The number of moles now I'm going to get is this divided by this, divided by this, and this. So let's do that on the calculator. So I'm going to take 820.8 okay, yep. 820.8 divided by 760. Now that's the pressure. I want to divide also by 0.0821. And I want to divide by this left parenthesis. And the temperature is 341 plus 273.15 close. Now, I'm looking at my screen to be sure I got what it says here. 820.8 divided by 760 divided by 0.0821 divided by 341 plus 273.15. That should be good. So my number of moles I get to be 0.0214. And, you know, there's other digits in it, 19. Now, that's the number of moles. Now, so that many moles is equal to this many grams, 3.014. Yes. Divided by molecular weight. So if I take the mass divided by molecular weight, that gives me moles. So I can get the molecular weight by taking the 3.014 and dividing it by 0.0214 that I've got on my screen. So all I need to do is take 3.014, divide by that answer, and I come up with a molecular weight of 140.7139. Some more digits. And the molecular weight is listed as 141.
Dr. Pearson,
Yes.
why did you use 1 for the volume instead of the 0.860 liters?
Okay. You could do this, but the problem with it is if you use that volume, you have to use the density back up here to convert to grams from that volume. And then when you get to the bottom line here, where you're calculating number of moles, you have to use the number of grams you would have gotten for this many liters. Okay? So it's a harder problem done that way. What I noticed was, if it gives me the density, that's the density of that sample as well. So I can calculate everything based on the density. Now, if I wanted to go back later when I get done and see, well, how many moles would have gotten if I used this instead of 1 liter, you know, I'd multiply by that. So the knowing that the density is the same for any volume, I didn't need to use that at all. That's just, that's a complicating factor. And if you actually use that method, it'll take a little bit longer to get the problem. You can do it with that. But you got to remember, when you get ready to put the number of moles into the ideal gas equation, you have to use this density to calculate how many grams that volume would have in it. And it just makes it harder. But it would have worked the same way. But I know from the density that 1 liter weighs 3.014 grams. So I can use this 1 liter as my volume in the ideal gas equation. That makes that problem much easier. And when I get down to the result, I've got the number of moles in that 1 liter. And if I know the number of moles in that liter, and I know the mass of that liter, I can get the molecular weight like this. So this is the quicker way of getting it. But you could do it the other way as well if you wanted.
Okay.
It would work. It's just one or two more steps in it.
Thank you.
You're quite welcome. All right, let's look at number 5 and see. Okay, I will do the screen share so you can take a look at it too. All right, we're at number 5. Okay, at a fixed temperature in a movable piston, 0.25 moles of a gas occupies 206.0 milliliters. If one adds 1.250 moles of the same gas, and the final pressure is controlled to be exactly 1.5 times greater than the initial pressure, while maintaining a constant volume, a constant temperature, what will the new volume be? Okay, that's an awful wordy one, but translation is it's an ideal gas, and it's the general form of it where you have P1, V1 over N1 and T1. That's going to be R. This is the initial set. The final conditions would be P2 and V2 over N2 and T2. So the problem becomes one of just plugging in the data. So let's summarize what we know. We had the number of moles to start out with, this number, was 0.25. Okay, now what else do we know? We know the initial volume. That initial volume is 206, and it's milliliters, so we'll just remember that. Now, we're going to add 1.25 moles of gas. So the new volume, a new number of moles is 1.25 plus 0.25. That new volume is going to be 1.25, 0.25, 1.5 moles. 1.25 that we added plus the 0.25 we had gives us the new volume. And the final pressure is exactly 1.5 times the initial pressure. So this pressure is going to be 1.5 times P1. So I can replace that. And maintaining constant temperature. So T2 is the same thing as T1. Now let's go through and we can cancel out the P1 from here and here, the T1 from here and here. And when we're done, we're going to have 206 divided by 0.25 equals 1.5 times V2. That's what we're trying to calculate. What would be the new volume? Divided by 1.5. I have 1.5 here, 1.5 here. Now the 1.5 from here was from up back here. But that makes our problem a little easier. It looks like all I got to do is divide this out, and I should be good. So if I take 206 and divide by 0.25, works best if you turn the calculator on. 206 divided by 0.25. That comes out to be 824. And it'll be in milliliter units because that's what this was in, was milliliters. So 824, that's response A on the test. So we are in agreement with that. Okay, that's oh, I see, my got so small I couldn't find my share screen. Okay, Now, here we go. Ready for number 6? Okay, number 6 says, one would predict that reaction of magnesium hydroxide with chlorine trioxide would produce what? Okay, let's talk about this one. I'm going to mix together magnesium hydroxide. Now, magnesium hydroxide is a base. So, well, maybe I better get over here. Number 6. So I'm going to get magnesium hydroxide. And now I'm going to react that with dichlorine, Cl2O3. And I want to know, what do I expect for the product? Well, it's kind of setting us up that if this is a base, we want to treat this like an acid, probably. That's at least one thing. And it is true that if I were to take a metal oxide, for example, like magnesium oxide, and I put that into water, the metal oxides form bases. And they'll form this base in water when I put MgO with water. Now, non-metal oxides form acids. So if I put Cl2O3 into water, I'm going to make one of the oxychlorine acids, HOClX. And I don't know which one that would be. Well, here's how you tell. These acids are HOCl, HOClO, HClO2, HOClO2, that's HClO3, and HOClO3, that's HClO4. So this is hypochlorite, so this is hypochlorous acid. This is chlorite, that would be chlorous acid. HClO3 is chloric acid, and HClO4 is perchloric acid. So when you mix this particular oxide, you're going to make one of these. The way you tell which one is you look at the charge that it has here. Oxygen is -2, so that means the chlorine is +3 in this compound. If you look at the charge of the chlorine in this one, oxygen is -1, and oxygen is -2, hydrogen is +1. The chlorine in this one would be +1. It'll be +3 in this one, +5 in this one, +7 in this one. The one that we're going to make is this one. So this is going to behave as if it were HClO2. +1, +3, +5, +7. Yeah, HClO2. So what you're going to make is the same thing you would make with this base and this acid. You do a double exchange reaction. The hydrogen from here would react with this to make water, and you would be left with a chloride ion. So the compound you're going to make with magnesium is magnesium ClO2, 2. Magnesium +2, and that's -1. So that's the product you would make in that. And so in general, if you've got a metal oxide, you would make the metal hydroxide with the same metal charge, +2. And if you got a non-metal oxide, you'll make the H non-metal oxygen, oxyacid, with the same charge that you had up there. Let's say I did a different example. Suppose I had SO2 and I put this into water. Well, this is +4. So I'm going to make either H2SO3 or H2SO4. How do I know which one I'll make when I put this into water? It's going to be the one that's +4. This one's +4. This one's +6. So if I put SO2 in water, it would make H2SO3. And so SO2 in aqueous solution is going to do the same thing that sulfurous acid would do. SO3 would be the other one. And SO3 gas, if you put that into water, it's the +6, you're going to make H2SO4. That's +6 sulfur in that one. So again, this might be, this is sort of a general concept that's being tested, is that metal oxides or hydroxides behave the same in water. Non-metal oxides or acids behave the same in water. So you can either react the oxide directly and you'll get the same product as you would if you reacted the appropriate acid. It'll give you the same product. Okay. The next question is, which one is least polar? And I can just list the answers. We've got NH3 is the first one, and we're looking for least polar. Oh, so NH3 is A, B is PH3, C is ASH3, and D is SBH3. Now, you see they've all got the same kinds of bonds, don't they? They've got an NH or a PH or ASH or SBH. And the hydrogens are the same. Their electronegativities for all of them is 2.1. Now, if I'm looking at this family on the periodic chart, top elements, nitrogen, phosphorus, arsenic, antimony. Now, you remember the order of electronegativity? How does it go? That's right, it increases toward the top. Okay, so the electronegativity is going to be the greatest for nitrogen, the least for antimony, and now I'm going to attach them all to hydrogens. So I'm going to get a polar bond, perhaps, between these two, and the difference in the electronegativity, this one we know is 2.1. This one we know is 3.0, if you look on the periodic chart, the way we did them. This one and hydrogen turned out to be the same, 2.1, and phosphorus was 2.1. And then arsenic is going to be less than that and less than that. So when you put these together, this one is going to be the most polar, because nitrogen is in group 1, first row. It's going to have the biggest electronegativity difference between hydrogen that any of them would have, be the most there. But don't jump on the bandwagon and say this one's going to be the least. It's not. This one's going to be the least. That's 0. So the bond moment in pH3 is 0 because they happen to have the same electronegativity. What you'll see then as you go on down, they will become more polar, but the direction of the dipole moment will be different. For example, up here, nitrogen was the more electronegative element, so its dipole moment points towards nitrogen. But in this one, hydrogen is more electronegative than this one. Remember, they're equal at 2.1. So this one's going to be less than 2.1. So the electronegativity direction changes. It's still polar, and it's going to still get more polar as you go down. But this is the most polar. This is the least, then this and this. Okay. So the answer for least is easy. It's this one. And the reason why it's this one, and I neglected the shape factor, but that's all the same. If we were to do the valence bond structure for each one of these, it would look like that with a lone pair of electrons there. So they're all shaped unsymmetrically, but only this one is not polar. All the rest of them are. Now, it would have been a little harder, but not that much harder to have asked you which one is the most polar. That you should have been able to figure out was that one. It would have taken a little more thinking to see what the order would be down here to go from one of these to the next. That would have been difficult. So it would have really been a difficult problem if I said, rank these 4 molecules in order of increasing or decreasing dipole moment. That would have been harder. The 2 endpoints would have been easy to get, but the 2 in the middle might not have been so easy. So depending on the way the question was worded, if I were going to ask you this question and have you rank them, I would make sure that this one, the one that had this one as the most polar and this one as the least polar, had these in the correct order. And none of the others had these in the right place with these in the in some different order. I wouldn't have done that, do you? Okay. All right. So be careful when you're looking at dipole moments. There are 2 things required. You have to have polar bonds. Now that is the first requirement. No matter what the shape of the molecule is, if the bonds aren't polar, it's not polar. But the second, if this one is satisfied, then you have to look for an unsymmetrical shape. Now, how did we decide unsymmetrical shape? Remember, if I've got an A, X, M, like that, every one of them is nonpolar. But if I've got an A, X, M, E, N, I have to build the shape, put on the lone pairs, and see if they are symmetrically arranged to each other. If they are, it's not polar. If they are not, it is polar.
Could you move your paper?
Yes.
Thank you.
Okay. All right. Let's see, where are we? I guess we did number 7 now. So we're looking to go to number 8.
Dr. Pearson,
Yes.
I had a real quick question while you're in between this. Just to clarify, so is this a replacement quiz?
Yes.
Like,
this is for the replacement quiz review.
so if this is lower than any other quiz, it will be dropped, and if it's higher, it will replace. Is that correct?
That's correct, but it does a double whammy. It also replaces a lowest exam score. So it's going to be graded 2 ways. It'll be graded like a quiz and like an exam. Typically what I do is I grade it like an exam out of 100 points. And then I take 1/4 of that as a quiz grade. And that's the best way of doing it. I could grade it like out of a quiz and then multiply by 4. I found out you'll get a better grade if I do it grading it like an exam and taking 1/4 of that as the quiz grade. So it'll be graded 2 ways. And if the quiz grade is greater than one of your quizzes, it replaces it. Or if you missed a quiz, it replaces it. And on an exam, if you've got a missed exam or if you have a low exam, this score replaces the lowest exam grade as well. And of course, if you missed an exam, it replaces it.
And if you have like higher exam grades, it'll just be dropped if it's lower?
Yeah, that's right. It doesn't hurt you. It can't hurt you at all, but it can certainly help. And so, you don't want to say, well, I can't do as well on this. It's comprehensive, blah, 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 and make yourself excuses not to take it. You don't have to if you don't want to, but hey, if I'm going to take it and it can help me and can't hurt me, I'm taking it.
Dr. Pearson, can I ask
Yeah.
another quick question to follow up on that? So the final is graded out of 150 and 100. So does that also replace?
Yes.
Okay.
The final exam will replace a second exam, but not a second quiz. It only replaces another exam. But the caveat also is the 150 point version of it counts. That can't be dropped. The final exams will be graded out of 150, and that grade will count no matter what it is. So it's not like the practice quiz. The review quiz, it won't hurt you if you don't do well. It just goes away. But if you don't do well on the final, it will hurt. It counts like 1.5 exams. So you really do want to do your very, very best on the final, because it can help, but it can also hurt. I've had a number of students that had a good solid A going into the final, and they thought, hey, I don't have to worry about it. I got an A. Well, they wound up with a B because they wound up scoring down at the 4th or 5th percentile on that final exam, which, you know, that's essentially a flat F. And when you average that in with an A, you're going to be lucky to get a B or a C. So don't blow the final off for sure. Okay.
Do you grade on a curve?
I'm sorry?
Do you grade on a curve whenever you grade the individual exams?
All of them are curved because of the way I've graded them. They're graded on a percentile ranking. So it's a little bit hard to explain, but you notice my grade scale, it's not linear. The number of points that you get for one question varies depending on how many questions you've already got right. So that's because it's graded like a standardized exam. If you took a standardized exam, like when you took the SAT or when you take the PCAT, it's graded like a percentile ranking. If you score at the 50th percentile, that means you beat half of the people that took it. If you scored at the 5th percentile, then you only beat 5 out of every 100 people that took the test. So that puts you way down on the list. Now, the way my grade scale works is the middle 2/3 of the class, it will be in a range where my scale says C. That's where it should be. The middle of the percentile distribution, plus or minus 1 standard deviation, should cover 64% of the class. So that's where the C range is. And then the rest of it is divided up. So the points that an individual question has depends on how many questions you had to get right on the test. So that's nonlinear, and it is in fact already curved. Now here's what I do. I don't tell people about it until it happens. So far it hasn't happened here, but I'm expecting it might happen on exam 4. When I grade exam 4, I know I've got some A students in there, and I know I'm expecting some people to get A's on that test. If nobody gets an A, or if there's not enough people getting A's, then what I'll do is go back and add a point, or maybe even 2 points, to everybody's score and have it regraded. And then if it shows up with a reasonable distribution of A's and B's, then I think that test is okay. And so you may see that when I post the grades of exam 4. Typically, I do have to adjust the grades on exam 4 a little. I typically don't adjust the grades on the final exam because it's more strict. The version I'm going to give you is very much like the American Chemical Society makes up standardized exams for Gen Chem 1 and Gen Chem 2. and actually for the whole course, 1 and 2. And you're going to be taking an exam like more than 3,000 students across the country took when they standardized that exam. And so that's going to already be curbed the way it should be. And I don't feel comfortable trying to adjust my class because I didn't do a good job of teaching it. I don't want to adjust my class against a standardized exam that's been judged outside. And so I won't probably adjust the grades on the final, but the replacement quiz and the 4th hour exam, I probably, I will if it's needed, because, you know, I know I've got a good group of students. I know that historically in the past, my summer school grade distribution is the best of the year. People tend to do better, even though it's crammed into such short amount of time. So it usually does work out okay, but I will probably adjust exam 4 if it's needed. I will adjust the replacement quiz if it's needed, but I won't adjust the final exam.
So technically we have 2 exams that could be replaced if we do.
You have
well
up to, you have 2 exams that can be replaced, yes.
Okay.
So now, can we talk? What I did this for a deliberate reason, because in my early parts of my career, I noticed that I had some students that started out weak or not devoted, or I don't know why, but they weren't doing well in the first part of the course. But by the end of the course, they were really hitting on all cylinders. They were doing really good. And I could look at the 3rd and 4th hour exam and I could see the level that they were taking out to Gen Chem 2, let's say. And they weren't getting a grade that was more like how they finished the course, because that bad beginning was averaged into it. So I came up with the idea of the replacement exam and using the final as a replacement, so that if you had a couple of exams early that you didn't do well on, but you know the material now, then I felt comfortable with replacing those old exams. And I feel good about the grade that I'm giving at the end of the course is an indicator of what the student actually finished the course with. So that was my philosophy for doing it. And I really do like it. I usually get a grade distribution that I think is reasonable and very well. And most of the time, I can almost guarantee you that if you go on in chemistry, you will not make a grade lower than you make in my course, no matter what course you take. That's usually the way it goes. So I feel good about that. Okay, now, all right, let's go on with number 8. Recording all of this is going to take forever. All right, number 8. We want to predict a reaction and determine whether we think it takes place or not. Here are the 2 reactions. We've got Na2, 3, PO4, and 2 of those going to 2Na2O and P2O5. So that's number 1. And number 2, we've got S plus 3 I2s going to SI6. And solid, solid, solid. And this was a solid, this is a solid, and this is a solid. Okay, so let's look at the 2 reactions and see if we think they'll take place. Now, if I'm looking at these and from your perspective, I'm thinking, well, how in the world am I going to know? We could just pull out any old reaction you wanted to, and how am I to know whether it's going to take place? That's true. But when you get further on in chemistry, you could look at these two reactions and instantly know whether they take place or not, because it comes from experience and that builds up over time. You haven't had the time. So what are you looking for? Well, what I'm looking at this reaction, it's a decomposition reaction. And it's making an oxide of a metal and an oxide of a non-metal. Now, I know the oxide of a metal will make a base, a hydroxide base. I know the oxide of of a non-metal is going to make an acid. Now, an acid and a base will react this way. We know that reaction always happens, so this is not likely to occur. But I looked at each one of them. Now, let me tell you what this stuff is. This stuff is your dishwasher detergent. That's what it's sodium phosphate. They say it's trisodium phosphate. It's not. That's named wrong. But if you look on the bottle, it'll probably say trisodium phosphate as the active ingredient in it. Well, does your dishwashing detergent decompose sitting under your sink? No. So this is not going to happen. Now, you might not have known that your dishwashing detergent was this, and so you couldn't have made that analogy. But you could look at this product and see, well, this would make a base and this would make an acid. They are not going to be stable together. It's going to go back the other way. So this reaction going from left to right would not happen. The one going from right to left would. Now let's look at this. A couple of things I would look for first. Sulfur's in group 6, oxygen in group 7. So as a metal end of a formula, sulfur could be +6 and iodine could be -1. The formula is okay. So it is possible that the reaction could take place. But let's think about what we're doing. The sulfur atom is in the second row, but iodine is way down here. So iodine is a great big ion like that. What's the likelihood of putting 6 of these with one of those? Not very good, is it? Now, it's possible, but I don't think you can make that compound. I've never seen it made, but I don't know. I've not seen all the chemistry. But if I'm looking at, say, sulfur, that size, and fluorine, even smaller, then is it likely you could put 6 of these with one of these, sulfur and fluorine? Yes. If you just mix sulfur and fluorine together, you will make SF6. That compound does exist and happen. So the key to me for this question is which one of those would occur readily at room temperature? Well, I know this one's not. This one probably not either. So my guess for this reaction would be neither one of them would occur readily. This one, I would say, might happen. This one's not going to happen at room temperature for sure, because you'd have to heat that stuff up probably 700-800 degrees, I'll bet, before you would decompose it to this. And I don't think that's likely to happen. Okay, but again, how do you prepare for that one? The preparation is just what I told you. Look at the reactions, see if you can figure out why a reaction might happen or might not happen. Look at both the reactants and the products going from left to right and right to left, and see which one you think would be the most likely way for the reaction to occur. I would imagine in this one also, if you ever made this, just the slightest heating or whatever might cause it to do that, go back the other way, because that bond would be so weak between the little tiny sulfur atom and the great big iodine atom. So again, look at it both ways and make your best judgment. It'll get easier as you go along.
Dr. Pearson, can I ask a quick question?
Sure.
Just to abate any of my anxiety about the final tomorrow. And I'm sorry if you answered this question yesterday. But is the actual final tomorrow, so not your final quiz, but the final, is that going to be set up the same way that you've done finals, so 30 questions by 55 minutes, or will there be more questions?
I think there's 40 questions on the final, but there's a lot of visual questions. That is, you're going to be looking at a picture and saying something about it. When we look at the final exam after we finish this, if we get time, I'll look at it and I'll point out those. So there are more questions, but it really will take a lot less time per question on the final. There's a lot of them that's visual and quick. So don't be anxious about it, because it will not be nearly as stressful taking that final as the exam you just took. Not even close. So if you were able to finish this one in 55 minutes, you probably will have 55 minutes. Well, actually on the final, we give exactly 60 minutes. So you will have exactly 60 minutes to do that test, and it will be a lot quicker. So I think when we look at the practice final exam, you'll see what I'm talking about. But yes, it will. Each of them will be an hour, and of course, I mentioned it earlier. I don't know, maybe it was before we got started, but the plan tomorrow will be the review quiz will be the 7:30 version. That will take 55 minutes, and that would get us out about 8:25. Somewhere around 10 o'clock, I'll tell you sooner. I'll tell you after we, let's see. I wanted to give you some time, and I wanted to give you, we should, let's say 10:30. So I'll make a note to myself. At 10:30 tomorrow, we'll do the final. So I'll set that up on D2L to open at 10:30 for everybody without the special access. Special access will open at 10. And I'll set that up on D2L after we finish today. And neither the replacement test nor the final exam will become visible to you until tomorrow. So they'll remain invisible until maybe 6 o'clock or 6:30 tomorrow. I'll open it up so they become visible. Okay, all right, we're number 9.
Thank you.
Sure. And let's see, I do need to, I probably ought to screen share that with you so you can see what it looks like. Okay, now let's make this bigger, because make it easier for you to read. Okay, easier for me to read. All right. Oh, I see something I can do to save us some space. We don't need that much space in that column. All right, now. Okay, down. And okay, that's going to cover most of it. Okay, now we're ready for number 9, and it's the set of 4 quantum numbers to identify the second 2p electron in sulfur. So it's the quantum numbers for the second 2p electron in sulfur. Okay, so let's go over here and think about what we're doing. Now, sulfur is element, it's right under oxygen. So on the periodic chart, we got oxygen and sulfur in group 6. Okay, so we're going across the 2p level, and in sulfur, it'll be, and oxygen, everything in group 6, it'll be we're in sulfur, so this is the 2p, this is the 3p. So we're talking about this row up here now for sulfur, it's going to be filled. So if I go, this is 2p, this is +1 and 0 and -1. The second 2p electron is that one. Now in sulfur, the rest, you know, they're all full. So at the 2p level, sulfur's in the 3p row. So that means its 2p level is completely full. But we're looking at the second electron, it's that one right there. And so N is equal to 2. That's 2. The L is equal to 1. That's for p orbitals. The M, or M sub L, is equal to 0. And the spin is equal to +1/2. So there's the set of 4 quantum numbers for the second 2p electron. So it's 2, 1, 0, and spin +1/2. So let's see if I can see what that answer is. 2, 1, 0, 2, 1, 0 +1/2. That'll be D on the test. So that should be the correct answer for it. Okay, number 10. The predicted ground state electron configuration for europium, number 63. So we want to go number 10. We want to get the electron configuration. And we want it for europium. And we're told it's element number 63. All right, so let's look at how we would do that. Now, europium is number 60. What did it say 63? Yeah, there it is. There, I see it. It's right there. So europium is 63. Now I'm going to look at the noble gases. I want the one that's the biggest, but less than 63. So if I'm looking over here, xenon is 54 and radon is 86. So xenon is going to be the core. So I've got part of it already. It's going to be the xenon core. I guess if I'm taking an exam, I'm going to check that to be sure I can. Okay, I can't eliminate anything. Didn't think I could, but you know, who knows? Okay, xenon core. After we go to xenon, now we're right here, we're going to go across row 6. So that's 6s2 when I get to barium. So we're doing 6s2. Well, you know what? I think I can eliminate some answers. Oh, yeah. In fact, I can eliminate C and I can eliminate D, I think. Yes. And So it's either A or B, and I'll show you what they are in a moment.
Dr. Pearson,
Yes.
I have a question. So sometimes whenever we're trying to find the electron configuration, we only put one, even though the s orbital fills up first, sometimes we only put one there, and then we move that electron into the next orbital.
That only happens for, the only ones we're going to let that happen is for chromium and its family and copper and its family. So
Okay.
you don't think about doing that in any other cases. Now, the honest truth is it does happen several places on the chart, but it happens routinely always for elements in those two families.
Chromium
So
and copper.
that's the only ones, chromium and its family, and copper and its family, the only ones we're going to deal with.
Otherwise, we're going to let this.
Let the periodic chart tell us. Yeah, we're going to follow the yellow brick road. So here we go. Now we're at element 56, and now we go to 57. That's lanthanum, and it's in the d orbitals. So that's 3D, 4D, 5D. So it's going to be 5D. The first orbital to take an electron is the +2 level, the +2 one. We're going to put one in there. And then we go to 58, which is down here. Now that's 4F, and we're going over to europium. 1, 2, 3, 4, 5, 6. So it's going to be a 4F with 6 in it. And technically, I would need to break these 6 up to where they go, but there's 7 of the orbitals, and the first 6 of them will have 1 electron in it if we needed to do that. I'm seeing on this that the F levels are not broken up. So what we expected to have is 6, we have xenon, we have the 6s2, we have the 5d orbital is going to have 1, it's the +2 component of it, and the 4f is going to have 6 in it. So that should be the answer. 6s2, 5d. Okay. I do this sometimes just to make people think, and I did it there. This looks like let's see, what did they say the correct answer is? Looks like to me they are showing the s orbitals moving into the d orbitals, and let's see if that's true. I think I did the Google answer to, what are we doing, number 10? No, it's A. Who says it? Oh, I see. Yeah. Okay, it's for the same reason though. You see the 6s2, this was 6. So this is one of those examples. I would not do this on an exam, but on this practice test, I wanted you to question why you did that. And if I move that 1 electron out of the d orbital and put it over here to 7, then that's a filled half shell, and we've got rid of that empty, with that shell with 1 in it. So this is a case where that would happen, but I wouldn't expect you to know that. So the Googled correct answer for europium is this configuration. I can understand why it is, because I could move that 1 electron into the f orbital and create a half-filled f orbital. So don't look for that on your test. I won't do that. I will follow the yellow brick road, except in the case of chromium and copper. And chromium and its family, copper and its family, those will have S jumping into D. But I told you it happens a lot the rest of the places, but you're not responsible to know that. I just put it on here. And mainly I did expecting people to get what I had here. And then I gave the correct one that's Googled, and you could see why. that one electron moving from this partially filled orbital into this one gets rid of that orbital and makes this one half full. So you've got filled and half filled shells for everything in the valence area. And that is correct, but that's not what I would have expected you to get. And it won't be one of the answers on your test. On your test, I will give the correct yellow brick road answer, and I won't do anything with reality.
Quick question. So for the europium, would the N number have been 4 then, since it's a 4f orbital?
It's the 4f orbital, yes.
So the
Now,
N
the way
number was 4.
the way you can remember that is the first row of p orbitals is 2, the first row of d orbitals is 3, and the first row of f orbitals is 4. So first row of s orbitals is 1, p orbitals are 2, d orbitals are 3, f orbitals are 4. So when you're looking in those regions on the periodic chart, you can tell, say if I'm in a p region, I want to count from 2. The first row will be 2, second row 3, 4, 5, 6, and so forth. And then if you're looking down at the bottom in the f orbital region, first row is 4f, and then 5f. And in the d orbital region, the first row is 3d, 4d, 5d, like that. Now, the side of the chart, we had the rows numbered. So group 1 and 2 is only going to have s and p orbitals. For 2, no p orbitals for row 1. And then 3, you'll have 3s and 3p, and 3s and 3p and 3d, and then so forth. So no, you would be 4s by the time you get down to the 3d. It will be in the 4th row. So you can tell on the periodic chart. If you look back in your lecture notes when we went over that, I had each row labeled with where they what their quantum number is for that row. Okay, number 11 now deals with size of atoms, and we're looking at essentially strontium and rubidium and selenium 2 minus and strontium 2 plus. So we want to compare the size of strontium and rubidium. Now again, you have to look at the periodic chart. Okay. Strontium is here, rubidium is here. What's the relative size? Size decreases going across. Remember, it decreases going across. So strontium is smaller than rubidium. So strontium is less than rubidium. Now let's look about the ions. Here's selenium right here. Selenium minus 2 is like krypton. And strontium plus 2 is like krypton. So these are both like krypton. So they're isoelectronic with each other. So the more negative the charge, the bigger they are, because they got the same number of protons. So they got the same number of electrons, but this has fewer protons than this one. So this one is bigger than this one. So to compare these two, I'm looking for a comparison. It's got strontium. Okay, it's doing the greater than. So this, in this case, it would be RB is greater than SR. So that's what I'm looking for somewhere. Okay, so C, that's true, and B, that's true. So B or C satisfies this one. Now, when I'm going to, I'm doing greater than, so it's that order there. So I'm looking for an answer that's SE greater, SE minus, in either B or C. So element SE minus greater than, okay, so of these two, I was comparing B and C. B doesn't work. C is then the correct answer. No, I'm sorry. This thing is backwards. It's got B and C. SE greater than, SE2 minus greater than this is in response B, but C has them reversed. So the correct answer then would be B. It would have RB greater than SR and SE greater than SR2, SE2 minus greater than SR2 plus. So that's right. So in this comparison, if you're dealing with non-charged species, you're going to look at the order on the periodic chart. And just to remind you, you're going to get much bigger differences across this first row than you will across the other row. Now on any row, the size is decreasing across any row, but you're increasing going downward. And the row that you're on is more important than the column that you're in. So for example, if I'm going with an element, say down here on the periodic chart, compared to anything above it, it's bigger. Even though they get smaller going across, it's still going to be bigger than anything in the rows above it. That's the rule we're going to use. And that will work almost all the time. But that allows you then to make a lot of comparisons when you're just looking at position on the periodic chart. Number 12 is to compare lithium and iodine and calcium and argon with the energy required to remove an electron. So we're talking about the ionization potential. How does the ionization potential go? Well, we know that it increases as you go across a period, and it decreases as you go down a column. So that's the general trend for the ionization potential. But there are some points where things are different. We're looking at lithium and iodine. Okay, so if I'm looking at lithium, it's way up here at the top. And I'm looking at iodine, which is way down here at the bottom. And I want to compare which of those would be would be easier to remove an electron from. Well, I've got lithium is that size, and it's got an electron there. And iodine is that size, so it's got an electron there. The electron's going to be much further apart, further out in that one than it is in lithium. Now, let's we're moving an electron from the outside of that atom or from the outside of that atom. Now, I'm going to look at this first. I'm going to say, okay, what usually happens when they react? Well, lithium forms a +1 ion readily. What usually happens when iodine reacts? It forms a -1 ion. So you see, I'm expecting lithium, even though it's smaller, to have a lower ionization potential than iodine does because of the nature of the stuff. This is a metal. Metals generally have low ionization potentials. Non-metals have higher ionization potential. So I'm expecting those values. I'm expecting lithium to be less than iodine. Okay, that's my best guess. Might be wrong, but that's my best guess anyhow. Okay, now, And I've got both choices. I've got lithium greater than iodine and lithium less than iodine. I'm expecting lithium to be less than iodine, or iodine to be greater than lithium. And that's B and D on this test.
So an element that's more likely to take an electron, you consider that a higher ionization potential. Is that the wording?
Yes, I'm expecting if something likes to form a cation, like a metal, it's going to have a low ionization potential because it likes to do that. It likes to form a positive ion and give up an electron. So it should be pretty easily to get an electron away from a metal. And I'm guessing that non-metals, since they tend to form negative ions, they attract more electrons than what they've got. So it would be a little higher ionization potential, I would guess, for a non-metal, virtually any non-metal, to remove an electron from it would be a little bit harder than it would from a metal. So that's how I'm making that judgment. Now, let's look at argon. The other pair is argon and calcium plus 2. If I look on the periodic chart, calcium is right there. Taking 2 electrons makes that argon. So this is also an argon-like species. But now, argon is, how many protons we got for argon? That's what, 18? Yeah, 18. Element number 18. And calcium is number 20. So they've got the same number of electrons, but this one's got 20 charges on its nucleus, 20 positive charges, and this one's got 18. So it's going to be much harder to take an electron out of calcium plus 2 than it would out of argon. So calcium plus 2 should be greater than argon. And we're looking at B and D. Calcium greater than argon is D. So that one fits both criteria. Let's see. Okay. We'll go a few more minutes and maybe take a little break. Let's try to get the halfway point. All right, we're at 13 now. Let's I'll show it to you. Okay. Number 13, we've got the reaction is 2NaNO3. It's going to go to 2NaNO2 plus O2. So this is reaction for decomposition of NaNO3. We got molecular weight of each of the substances given. And the question is, what volume would be at STP, standard temperature and pressure. The pressure is 1 atmosphere, and the temperature, standard temperature, is 0 degrees Celsius. And we use this so often that the volume of any gas at standard temperature and pressure is 22.4 liters. Okay, so let's go over and let's work out the problem then. All right, so here's our reaction, and we want to know what volume at STP would I get. So I'm going to ask first, anytime I'm dealing with a gas, I'm going to ask first moles. Okay, now I have 153 grams of sodium nitrate. The equation is showing 2 moles of sodium nitrate, and the molecular mass is given at 85. grams. So there's my RBF. So my number of moles of O2 is going to be my RBF 153 divided by 2 and divided by 85. And that's going to be, and then that's going to be multiplied by the number of moles shown in the balance equation is 1. So that's going to be my moles. Okay, so 153 divided by 2 and divided by 85 is 0.9. So I get 0.9 moles. And now if I know this STP comparison, I know that 1 mole is 22.4 liters. Now, if I know that, the question, the answer is real quick. I just times 22.4 and that comes out to be 20.2. And that would be response A on the exam. Now, if I didn't know that, this 22.4 connection, if you didn't remember that, I don't emphasize it a lot in the lecture, but it is mentioned in the textbook, and there are examples like that. If I didn't know that, I would say V equals nRT over P, and I've got the number of moles. That was what I got. I got 0.9, wherever it was right there. So I'm going to put the 0.9 in here. 0.0821, temperature is 273.15, pressure is 1 atmosphere. I'm going to multiply that out and I'll get the same answer. So if you don't remember that relationship, I think it was on that list of constants and stuff that was at the top. But if you don't remember that, you can do this. That would work the same way, give you the same answer, and not be much more difficult, really. 0.9 times 0.0821 times 273 divided by 1. So whether you remember that or do it this way doesn't matter. And in fact, that's why I don't emphasize it that much. It's not a big deal. It doesn't save you a lot of time. But there are some numbers that I keep in mind. I do that one. I do keep 22.4 liters per mole at STP. But what if you're not at STP? What if you're at room temperature? Well, I've done that calculation so much, I remember that one as well. It's 24.4. So 22.4 at 0 degrees and 24.4 at room temperature. So for me, one is just as good as the other. In fact, I probably use the 24.4 more often because most of the time we do the temperature at 25 degrees instead of at 0 degrees. Okay. Let's look at the next one. This is number 14. And you've got we got a reaction to AgNO3, silver nitrate, and sodium carbonate, Na2CO3. And we make silver carbonate, Ag2CO3 plus NaNO3, 2 of them. Okay. Now let's see what we're asked. I've got what volume of silver nitrate, and the molarity is 0.168 molar. I'll show you my paper in just a minute. I just want to copy stuff down. And then I'm reacting 84 milliliters of 0.252 molar of this, and we want to see what volume that's required. So let's stop the share. I've got everything set up on the paper. There's my reaction to silver nitrates. We want to know the volume of 0.168 molar that would react with 84 milliliters of 0.252 molar sodium carbonate. So if I multiply 84.4 times 10 negative 3, that's 84.4 liters times molarity, that'll be moles. The equation is showing 1 mole. The equation over here is showing 2 moles. So the number of moles of my AgNO3 that I'm going to need is going to be my rebalancing factor here. It's 84.0 times 10 minus 3 times the molarity, 0.252 divided by 1. Now that's the rebalancing factor, times 2. So that's going to give me my moles of silver nitrate that I need. So I want to be sure that I'm copying my numbers correctly. So I've got 84 with an exponent of negative 3. I want to multiply that times the molarity, 0.252. When I do that, that comes out to be 0.021168 divided by 1, and then times 2. So my moles of silver nitrate is 0.042336. That's equal to the volume times the molarity. Molarity of this solution is 0.168. Okay, so I can solve for the volume. It's going to be my rebalancing, my number of moles here. And I want to divide it by 0.168. And that's going to give me an answer in liters. So I take that rebalancing factor on my screen, divide it by 0.168, and I get 0.252 liters. And the answers are given in milliliters, so this is liters and milliliters, and milli is 10 to the negative 3. So I want to take this answer and divide by 1 with an exponent of minus 3. And I get 252, we expected. So it's 252 milliliters. And that's response C on the test, so we're good. I think I can do the other one, the number 15, is it asks us for the correct Lewis dot structure of O2F2. Now, that's obviously not directly, anyhow, a central atom problem. We might convert it to one because we might be able to do some stuff with this. But here's what I'm going to do. I'm going to use the Tinker Toy model. For oxygen, I want every oxygen to have 2 lone pairs and a bond. I want 2 bonds. And I want every fluorine to have 1 bond to each fluorine. So if I'm looking at this, the best arrangement is going to be OOFF. I want the fluorines to be on the end. I can connect the 2 atoms together like that. I want 2 lone pairs on every oxygen. Now that's the structure that we would probably like to draw. Let's just double check and be sure that that's got the right number of valence electrons. There's 2 oxygens, oxygen in group 6. So there's 12 electrons from the oxygen. There's 2 fluorines, fluorines in group 7. There is 14 electrons for them. So that's 26 electrons altogether. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So that structure does work. And so that's what that Lewis structure should look like. And let me share a screen with you, and you can see I think that's it right there. You can see what the choices were. And the one that we said works is C. Now, this one wouldn't have the right number of bonds on oxygen. See, it's got 3 bonds and 2 pairs. That's not right. Oxygen can never have more than 8. 2, 4, 6, 8, 10. That's 10 electrons. Sulfur could perhaps do that, but oxygen certainly can't. And you could draw a structure like this, except you can't have a fluorine with 2 bonds. So that might look good, but it's not good because fluorine's got more than 1 bond. The only one that satisfies everything is this one. The fluorines have 3 pairs and a bond, both of them. The oxygens have 2 pairs and 2 bonds, both of them. So that's the only structure that works in that one. Now, someone asked me about the final exam, and it looks like the practical exam too has some visual questions like that. Now you see, this is one of the questions you could look at and immediately reject that answer because you can't have fluorine with 2 bonds and you can't have an oxygen with just 1. You could reject that answer right away because the number of bonds on oxygen is wrong. You can't have fluorine in the middle of a molecule. So you could eliminate all of these answers and center on this one visually. You don't have to do any math at all. You don't even have to do what I did over here on the paper to predict the structure. It was already given for you, and it would be easy to eliminate these questions. So that's kind of a strategy that you should use in going through the tests. I've talked about that before. And okay, so what I want to do now is I want to stop the video. No, I don't want to stop the video. I want to go to pause the recording. And we're now going to be working with number 16. Okay. And looks like the next few of them are probably going to be about things that we can do from the paper. So, I never did show you well, I can do it. I've got the paper already up, so let's go from here. Okay, number 16 is bromide ion. And it wants to know about what the shape of the bromide ion is. So we're going to do the VSEPR notation to get that. Bromine is in group 7. There's 3 oxygens in group 6. And there's 1 extra electron from the charge. So 3 times 6 is 18, plus 1 is 19, and 7 would be 26. So this is 26 valence electrons. We divide by 8. That gives us 3, 24, with a remainder 2. 2 divided by 2 is 1. So this is an AX3E type structure. And let's just go ahead and complete it. That'll answer maybe a couple of questions, or I don't know. So what we have is we've got bromine as our central atom. We do have 1 lone pair. There's 4 things attached to it. 3 plus 1 is 4. So it's a tetrahedral arrangement with bromine in the middle, with one of the positions a lone pair, and the 3 oxygen atoms in the other positions. And if we completed the structure, then we would need lone pairs on each of the oxygens. And that should have our correct number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. See, Daisy, I'm counting wrong. 3 and 1 is 4. That's right. That's right. And that should be correct. So I must have met just 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. It's 26. I counted it wrong first time. So that's what the structure looks like. And now the question for it is the molecular shape. The choices are trigonal planar. No. They are, it's tetrahedral. Electronic shape, but not the shape of the molecule. The shape of the molecule is trigonal pyramidal. That would be D. So you're going to have to do a different molecule, I guess. Yeah. For 17, we're going to determine whether the molecule is polar or non-polar. So, NO3 minus and ClO2 minus. Let's do them both by the math method and see what we come up with. Nitrogen's in group 5. We've got 3 oxygens in group 6 plus 1. 18 plus 1 is 19, and 5 would be 24. 24 valence electrons for this. 8 would go 3 times, and 24, 0. Divided by 2 is 0. NO3 is trigonal planar. No lone pairs means there's going to be a double bond to one of them. There'll be some resonance structures available for this, of course. Okay, and so that's what it looks like. It's an AX3, and the general answer for anything with no lone pairs is not polar. And you see this structure is symmetrical as well. And so that's not polar. So this structure is not polar. Cl2O, chlorine's in group 7, and 2 oxygens in group 6, plus 1 more electron. 12, 13, and 7, this would be 20. Divided by 8, it's going to be 2, be 16, and 4 divided by 2 is 2. It's an AX2E2. That's tetrahedral. I'm going to put 2 lone pairs on, so maybe I'll put them here and here. I'm going to put the chlorine here, the oxygen here, and the oxygen here. Now, this is polar because all 4 things aren't the same that's attached to the chlorine atom. 2 of them are oxygens and 2 of them are lone pairs. So it is polar. So NO3 is non-polar, and ClO2 is polar. So that would be, which answer is that on this one? That's C. NO3 minus is not polar, and ClO2 is polar. That's response C. This is number 18. We're going to get SO2, and we want to know the hybridization. At the sulfur atom. What kind of hybrid orbitals do we use? Well, sulfur's in group 6, and we've got 2 oxygens in group 6, So that's going to be a total of 18 electrons. Take 18, divide by 8. That's 2. 16 and 2 divided by 2 is 1. So it's an AX2E1. So now, if I'm looking at my SP, the d orbital is not going to be involved, but that's D and P and S. So I'm going to need 3. So I'm going to take one here and one here and one here. It's going to be SP2. And SP2 is in this trigonal planar shape. If I want to put the sulfur here, it will have one lone pair here and an oxygen here. And of course, there'll be resonance structures. One of them would be formally a double bond and one would be a single bond, but you know, it resonates between the two. So this is what the shape looks like. The hybridization needs 2 plus 1 is 3. And I need to put 3 orbitals in that. One of them will be S and 2 of them will be P. So it's SP2 hybridization. And 3 things is trigonal planar for the electronic structure. So that's got everything. So the correct answer to this one, SP2, is the A response on the exam. Okay, and moving right along. Number 19. Oh boy, I gave you some exercise on unit conversions, but it'll illustrate a point. Okay, we've got given 6.47 times 10 to the 4th, and the units are kilograms per kilometer squared. And we want to convert that to pounds per square mile. Okay, so we've got a ways to go. I'm going to go to kilograms to pounds. The only way I know to do is go kilograms to grams and grams to pounds. I'm good there. Now, the kilometers, I'm going to go to meters. That's going to be okay. I mean, I just replace the K with 10 to the 3rd. And we're going to go from meters. I'm going to go to centimeters because I know how to go from centimeters to inches. Then I know how to go from inches to feet. And then I know how to go from feet to miles. Okay, so let's string it out. Here we go. 6.47 times 10 to the 4th. Kilograms, I'm going to change that times 10 to the 3rd. Got rid of kilo, and now that's grams. Now, I want to go from grams to pounds. I can do that because I remember there's 454 grams in 1 pound. Now, at this stage, I've got pounds where I want them to be in the numerator, so I'm done with this part of the conversion. But I got to go this way now. So I'm just going to string all the factors on, and I'll keep stringing them when I run out of space. Well, I've got kilometers, and that's squared. Well, I'm going to replace kilo with what it's equal to. So that right there is a 10 to the 3rd. Now I've got meters squared. I've got to go from meters to centimeters. And I know that this is 10 to the minus 2, so I'm going to put a 10 minus 2 down here. And now the whole thing is squared. Now I've got centimeters. Now I'm going to go to inches. So I want centimeters down here. I want inches right there. 1 inch is 2.54 centimeters, and that's squared. Now I'm to inches. I'm going to go down here, add this factor on from inches to feet. Inches are in the numerator, so I want inches in the denominator. I want feet here. 1 foot is 12 inches, and that's squared. Now I'm to here. Now I'm going to go from feet to miles. There's 5,280 feet in 1 mile, and that whole thing is squared. Okay, now, if I'm looking at this, I think I can go, maybe it'll look, wait, let's see. I've got 1 and 1 and 1 and 1 and 1. Looks like I've got a whole bunch of ones in the numerator. So I've got 6.47 times 10 to the 4th, 10 to the 3rd is 10 to the 7th. And then in my numerator, all my factors down through here are ones, but in the denominator, this first factor is 454. My next factor, it is that was from the grams to pounds conversion. Now I had kilometers squared, so I did have something to go up here, didn't I? I had a 10 to the 3rd kilometers, and that's squared. And now I went from, I replaced that. No, that's not it. It's just meters now. And then I'm going from meters to centimeters. So I got a 10 to the minus 2 centimeters down here. Where am I? Right there. And then I've got 2.54 down here. And that's squared. Wait, the 10 to the minus 2 was its, yes, it was squared. That's squared. I think all of these factors are squared. Okay, 2.54. The next one is 12, and that's squared. And the next one is 5,280, and that's squared. Okay. All right, so if I haven't screwed up somewhere, I do all this on the calculator, I should get the correct answer. So 6.47 with an exponent of, wait, this is 7 out here. Why did I write a 3? That's 7. Okay. That was 6 point, that's kilograms. Oh, I see. That's kilograms. That's this, that's that part right there, just in kilograms. And then I wanted to go, yes. And then I want to divide by 454. That's right. But this should have been a 7 right there. So I am right. 6.47 times 10 to the 4th times 10 to the 3rd, 6.47 times 10 to the 7th. And that would be now in grams, and 454 grams to 1 pound. So that's good. And now that would give me, it's all tangled up. I think I would rather just turn my paper sideways so I can get all these factors in. I don't want to screw it up. So let's do it again. 6.47 times 10 to the fourth times 10 to the third. And now that's in grams. And it's grams per kilometer squared. Now we do our conversions. The first conversion I'm going to do is from grams to pounds. And there's 454 grams in 1 pound. Now I've got pounds per square kilometer. Pounds is where I want to be. Now I want to get rid of the kilometers. So what I'm going to do here, this was kilometers squared. So I'm going to replace that with 10 to the third meters, and that's squared. Now, that's giving me now pounds per square meter. Now I want to get rid of the meters, and I want to go to centimeters. And centi is 10 to the minus 2, so I need a 10 to the minus 2 there. Okay, 10 to the minus 2 meters is 1 centimeter. And now that will give me centimeters, and that factor squared. Now I want to go from centimeters to inches. 1 inch is 2.54 centimeters. So I've gotten rid of inches. No, I've gotten rid of centimeters. And that gave me inches. Now, I'm going to go from inches to feet. One of those is 12 inches. And now I want to go from inches, no, from feet. I got rid of inches, and I've got feet still left. I want to get rid of feet, put them right there. And 1 foot is, I just undid what I did. Where am I at? 2.54 centimeters squared to inches, 1 inch. Oh, yeah, that's what's wrong. Right here. This is 2.54 centimeters squared. I want centimeters down here to get rid of centimeters. I want inches up here, and 1 inch is 2.54 centimeters. Well, back up and fun again. I don't know why I'm having so much trouble with this, because I'm not carrying my units right. I've got grams here, and I've got kilograms, kilometers here. And so to get rid of grams, I want it here. I want to go pounds up here. That's right. There's 454 of those in one of those. Now I've got pounds per kilometer, and the kilometers is squared. So I want to go from kilometers to meters, and this is a 10 to the third. And now that'll get to meters. and that unit is squared. So now kilometers squared are gone, and now this is meters. Now we go again. And I've got meters up here, and I want to go to centimeters here. The centi is 10 to the minus 2, so I could replace that with a 10 to the minus 2. So the number of I'm getting rid of meters. Oh, this was kilometers to meters. Getting rid of meters to centimeters. There's 100 centimeters and 1 meter. Now, meters are gone. And I've got centimeters. Now I'm going to go from centimeters to inches. 1 inch is 2.54 centimeters. Now I've got centimeters gone. This factor is squared. Don't want to forget that. Now I've got centimeters up here. No, I've gotten rid of centimeters, haven't I? Yes, I got rid of centimeters. I've got inches down here. I want to get rid of inches, and I want to go to feet. And 1 inch, 1 foot is 12 inches, and that's squared. Now that gets rid of inches, leaves feet. Now my final factor is over here. I want to go from feet to miles. And there's 5,280 feet in 1 mile, and that's got to be squared. Okay, let's collect all our numbers now. 6.47 times 10 to the 7th times 1 pound divided by 454. Now, that's got pounds where we wanted them to be, and we've gotten rid of grams. We're still left with kilometers squared down here. Now, so I wanted to go from kilometers to there, so I want this factor. That's 1, and it's 10 to the 3rd, and that's squared. And now at the end of this stage, I've got meters. Meters squared is my unit down here. I'm going to put meters up here, and we had 1. We had 100 centimeters here, and this is squared, so that meters squared from here cancels meters squared from there. Now I've got centimeters here, I want centimeters there, I want inches here. One of those is 2.54 of those, and I've got to remember to square that factor right there. And then that's going to be gone, and that's going to be squared, and that's got to be squared. Now I'm going to inches, 1 inch, and feet. 1 foot is 12 inches, and that's squared, and inches is gone. Now feet squared. And now I'm going to go from feet to miles, and 1 mile is 5,280 feet. And that's squared, and that cancels that. And then I'm left with miles squared. So I've got my unit up at the top right here is pounds per square mile. So I think my data is okay. Let's go ahead now and do the math where I've got it, where I can read what I had written. 6.47 with an exponent of 7. Okay. And now I want to divide that by 454. I want to divide that by 1. Divide that by 1. No. Divide that by 1 with an exponent of 3 and squared. Now that takes me to here. I want to divide that by 100 squared. No. 100. Push the wrong button. Squared. Okay, that looks right. And I want to multiply that by 2.54 squared. And I want to multiply that by 12 squared. And multiply that by 5,280 squared. And now let's just look on my screen and see if I'm tracking. 6.47 times 10 to the 7th divided by 454. And divided by 1 exponent third squared. That's right. Divide that by 100 squared. Multiply that by 2.54 squared. Multiply that by 12 squared. And multiply that by 5,280 squared. Okay. And let's see if we come up with an answer that looks like it's possible. Okay, it's well, what do you know? Well, miracles never cease. Thank you, Lord. 3.69101. Oh, well, that's what I'm getting. So it's 3.69 times 10 to the 5th pounds per square mile. And that does turn out to be response D. Okay, well, the whole purpose of that was just to do this thing of unit analysis, and it forced you to do a bunch of them. You can see what a mess I made the first time through by not planning a little bit further ahead. But we got through it. Okay, now let's look at number 20 and see what we've got here. The average kinetic energy and the average velocity of nitrogen gas at 300 degrees. We're going to compare the kinetic energy average and the velocity for N2, NCl2 at the same temperature. Okay, so this is number 20. Let's talk about this. The kinetic energy is 1/2 mv squared. Now, that's kinetic energy for anything. And we showed that that was equal to 3/2 R times T. Independent of substance, independent of phase. So that means that this is going to be the same for both N2 and Cl2 because they're at the same temperature, 300 degrees. Now, if they hadn't been, and I would vary the temperature, then I would have rearranged this a little bit differently. But since these are the same, if I do this for nitrogen, and I do the same thing, 1/2 mv squared for chlorine, then this has to equal this. The 1/2 will cancel out. So the m of nitrogen times the velocity of nitrogen squared will be equal to the mass of the chlorine times the velocity of the chlorine squared. That's Graham's law, remember? Just written, and we rearranged it a slightly different way. But the average kinetic energy is just this. So the kinetic energy average is going to be the same for both nitrogen and chlorine if they're at the same temperature. So average kinetic energies are the same. That's either A or D on the exam. The other two have differences. So the average kinetic energy, and I'm sorry. Well, I guess C is also included. It says C is the average kinetic energy and the average velocities are the same for nitrogen and chlorine. Well, the first part of that's true. We've got yet to determine about the average velocity. But since C's the same, nitrogen's molecular weight is 28. Chlorine's molecular weight is 71. So if these have to be equal to the same number, that means this V squared of nitrogen has to be greater than this one. So velocity of N2 has to be greater than velocity of Cl2 in order that this number times this number be the same as this number times this number. So since this is bigger, I would need a smaller velocity here. This is smaller, I need a larger velocity here. So nitrogen is going to be moving faster than chlorine. So the average kinetic energy is the same. But it says, but the average velocity of nitrogen is less. That's wrong. So it has to be A. Let me screen share so you can see the choices up here, up close and personal. See, the average kinetic energies are the same, but the average velocity of nitrogen is greater. And the other one we were comparing with, the average energy are the same, but the average velocity of nitrogen is less. So the correct answer is A. And so that's just an application of essentially Graham's law, but it comes from the relationship that the kinetic energy of any substance is 3/2 RT. And that's the average per mole for that substance. Okay. Let's see what we do now with number 21. Okay, we're doing some math. Which answer has the correct number of significant figures? So okay. Okay, oh, what am I doing? There we go. Okay. And here are the two, here's the A problem. Let's see if it's rounded off correctly. We have problem given like this, 11.33 plus 1.3745, close the parenthesis, divided by 9.41. So the parenthesis is the first operation you have to do. So you have to add these two numbers together. So let's add the two numbers together. 11.33 plus 1.3745. What I get when I do this addition is 12.7045. And we're not ending the calculation here. We still got to divide by 9.41. But now I've got to talk about round off. If this division hadn't been taking place, where would I round this off? It's addition. This has 2 decimal places. That has 4. The answer would round off here to 2 decimal places. Now, if I'm going to do a division, I need to know significant figures, 1, 2, 3, 4. So it's 4 sig figs. So I want to divide that by a number with 3 sig figs. I've got 4 sig figs, 3 sig figs. Answer 3. I guess I could get to see if that the answer shown to 3 significant figures. So that one is round off right. I guess that must be the answer. But when I do this, I want to divide and be sure I get that number, 9.41. And I get 1, oh, okay. Helps if you push the right button. 7045. 12.7045 divided by 9.41. I get, the answer I get is 1.35010627. I'm rounding off to 3 significant figures of a report 1.35. Well, so A works. Let's be sure the others don't work. Now I've got, again, a parenthesis, 0.654. I want to add to that 9.862, close the parenthesis. I want to divide that by 12.68. All right, so here we go. 0.654 plus 9.862. This comes out to be 10.516. And now I've got 3 decimal places. I've got 3 decimal places. The answer would have 3 decimal places. So if I'm going to do a division now by 12.68, this has 1, 2, 3, 4, 5 sig figs. This has 4 sig figs. The answer should have 4 sig figs. And well, I'm running into a little bit of a problem right here. I'm coming out, the answer is shown 0.8293. Let's see if that's what I get. I've got this number and I want to divide it by 12.68. 0.8, so I'm getting 0.8293375394. And to 4 significant figures, it would be 0.8293. And that is what's reported. So, makes me think that I'm looking for the one that's not correct rather than the one that is. Both of those are okay. All right, we do 100.4 plus 9.2 and dividing that by 8.930. Okay, now we do the math. 100.4 plus 9.2. I come up with 109.6. And I've got 1 decimal. I've got 1 decimal. The answer should have 1 decimal. So that's right. But to do the division, 8.930, I need sig figs. I've got 1, 2, 3, 4 sig figs. And 1, 2, 3, 4 sig figs. The answer should have 4 sig figs. Well,
Okay.
yes,
It was a negative, a subtraction.
I'm sorry. Oh, thank you. Thank you, thank you, thank you. Let's see what difference that makes. It may not make any difference. I don't know. Let's see what it does. Let's do the math. It would make a difference in the answer, certainly. So it's 100.4 minus 9.2. It was a subtraction, yes. Okay, so difference. We got 91.3. And again, same argument, 1 decimal place, 1 decimal place, 1 decimal place. But now this is 3 sig figs. 3 sig figs and 4 sig figs. The answer should be 3 sig figs. And okay, now that one's going to be wrong. So I take 91.2 and divide that by 8.930. And I come up with 10.21276596. And I need 3 significant figures, so it should round there. So it should be reported 10.2. Should be the way it's reported. Okay, 10.21 is the way it's given in the problem. So C is not correct. I think this was, if the next one works out right, then we'll know that the problem should have said which answer has the incorrect number of significant figures. I've done it both ways. Okay, so this one, the problem is 213.56. The sign is plus this time. Plus 312.52. And we are now dividing that by 124.52. Okay, so let's do our addition. I notice the additions are both 2 decimal places, so my answer will have 213.56 plus 312.52. Okay. Oh, whoa. I entered that. 312 point, I copied, I don't know where I got that number, 312.64. 213.56, 312.64. Let's redo it. 213.56 plus 312.64. I'm coming out with 526.2 is what I'm showing on my calculator, but I have to have 2 decimal places, so I'll have to add that 0 in. My calculator truncates trailing zeros. Yours does too. So when I add these two together, the screen is showing 526.2, but I must have 2 decimal places in the answer. So I need that 0. Now I want to divide that 2 DEC and 2 DEC and 2 DEC. I want to divide by 124.52. Now, in the division, I've got 1, 2, 3, 4, 5 sig figs here. And 1, 2, 3, 4, 5. I've got 5 over here. The answer should have 5 sig figs. Okay, it doesn't. Okay, so there goes my theory. Okay, so I've got this number. I want to divide it by 124.52. Okay, got that answer, divided by 124.52. And my final answer is 4.2258 27176, 27176. And I need 5 significant figures, so it should be reported as, that should be a 6, 4.226 should be the way it gets reported. And it, oh, no, it's right. Oh, wait. I said 5 significant figures. Sorry, I screwed up. I just showed you 4. It should round off in the 5th significant figure. 1, 2, 3, 4, 5. So it should have 4 decimal places. So this should be 5, 8 is the way it should have been reported, and it was not. Well, I want to go back and double check these other two just to be sure that there is in fact a mistake, but I don't think there's, I'm sure there is. 11.33 plus 1.3745 . 11.33 plus 1.3745. That's right. Now I want to, and that should have had, I got 12.7045. That's right. That's what I got last time. I had 2 decimal places, 2 decimal places, 2 decimal places, 1, 2, 3, 4 significant figures. So that's good. I want to divide that by 9.41. And I do get 1.35016 whatever, but I've got 3 significant figures and 4 significant figures. Should be 3 significant figures, 1, 2, 3. So it should be reported as 1.35, and it in fact is. So that's okay. Now, let's do the next one is 0.654 plus 9.862. 654, 9.862 is that number, and that is 10.516. That's what I got. We had 3 decimal places and 3 decimal places, 3 decimal places. So that's 5 significant figures, 1, 2, 3, 4, 5. So I'm going to take that and I'm dividing it by 12.68. And what I get is 0.829337539.4. That is what I got. Now, we had 3 significant figures and 4 significant figures. The answer should be 3. Oh, that I guess I did it 4 a while ago, didn't I? No, that is right. This is 4 significant figures. This is 5 significant figures. 4 significant figures should be right. So 0.8293 is correct. So both of those are correct. So I'm going to fix this on my test so that it works right. And then I'll upload it to D2L. And what I'm going to do is I'm going to make this one wrong by giving it the least number of significant figures. That's probably what I would have done. So let's go to here, and I'm just going to take off the 3. Now that one is wrong, and only this A is correct. Let's see, what do we have for the answer for 21 down here? 21. Oh, it said B. Oh, okay. Well, let's go back and fix it the way it is. So B is correct. And I want to go back and put the 3 back on here that I had. That's 3. Let's make this one wrong. Let's make this one, well,
Can you see your screen, Dr. Pearson?
I'm sorry?
Can you see your computer screen?
Oh, yes. I'm not showing you what I'm doing on the screen. What I'm looking at is this one, and we saw that both of these 2 answers are correct. And the key says this one is correct. I wish it had been, you know what, I'm going to change it because this one, I guess it's 6 of one and half a dozen of the other. Does not really matter, but this one doesn't look like it would be correct, just looking at the numbers. So I'm going to go ahead and make this one wrong. And I'm going to do that by adding the next significant figure was a 0. So I'm going to put a 0 right on this one. Now that'll make it wrong. Okay, that'll make that one. Well, why? Okay, 0.35, 0. Okay, now, oh, I've got to make this format. I've got to make it a number with 3 decimal places. Or Excel will do the same thing my calculator does. It'll truncate off that 0. Okay, so now the correct answer is really, in fact, the correct answer. And I save that. I'll fix it and update it on D2L after we get done. All right. But it was a good exercise because I wanted you to understand about grouping symbols, how they have to do. I want you to understand when you round, where you would round off. If you've got addition and subtraction, it's by decimal places. So when you do the part that was the addition or subtraction, we had to note where our round off would be. You don't round off, you just note where it would be. And you count the number of significant figures. And then when you do the math, multiplication, and division, you round off the answer by the significant figures of the parts. And so I think doing 4 of these was good exercise, but if you already tried it, you probably wondered why A and B were both marked correct, both marked correct. Okay, now let's look at this one, and we can probably answer this one by looking at it. Potassium is element, maybe we don't, but if you had a periodic table next to you, you could. So I'll go ahead and show you. Okay, now potassium is right here. It's got 19 protons. So the isotope that we had for potassium, this is number 22. We had the potassium, it's the positive ion, and it's the 39 isotope. And it's element number 19. So that's its complete nuclide symbol. We had calcium, it's the +2 ion. It has 40, and it's element number 20. If you looked on the periodic table, potassium is right next to calcium. So calcium's 20, potassium's 19. The next element was scandium, and scandium is the 3+ ion, and its isotope 41 mass number. And if we look on the periodic table, scandium is element number 21. And then we look at, that's all, those 3 isotopes. They have the same number of something or other. Well, let's see let's see about neutrons. Subtract that number from that number, we get 20 neutrons in this one. And in this one, we get also 20 neutrons. And this one, when you subtract, we get 20 neutrons. So they have the same number of neutrons. And it says we're comparing neutrons and electrons. How many electrons would there be in each one? Well, if I take 19 and I subtract 1, it has 18 electrons. If I take 20 and subtract 2, it has 18 electrons. If I take 21 and subtract 3, it has 18 electrons. And so they have also the same number of electrons. So it says they have the same number. And if we go back to our share screen to look at the answers, it has the same number of electrons and neutrons. That would be C. They don't have the same number of protons. One had 19, 20, and 21. And protons only would certainly not work. So anything got protons, these two can't be right because they're different elements. Well, if I can eliminate protons, I eliminate all the answers but one. And, you know, actually that's probably the easiest way. I should have thought about that first. If I looked at my answers and saw protons, I should know that if you've got a different symbol, you got a different number of protons, because that's what the symbol represents. So they can't have the same number of protons. That eliminates 3 of the 4 answers. The only answer possible is a C answer. Okay, so that wasn't so bad. Okay, number 23. And what we're going to do is we're getting the percent of nitrogen in a compound is 36.9, and the percent of oxygen is 63.1. Now, if it only contains nitrogen and oxygen, I wouldn't have to give you both of those. You'd know what the other one was. And the exercise is, what is the empirical formula? Okay. The way we did that in the class is we said, okay, we're going to have NXOY is going to be the formula for this compound. And we want to figure out what it is. If I take the percent of nitrogen, it's 36.9. I'm sorry. Yes. Oh, you need to see the screen. Yes, thank you. The percent of nitrogen is 36.9. The percent of oxygen, excuse me, is 63.1. That's going to be equal to the number of nitrogens is X. The atomic weight of nitrogen is 14.01. The number of oxygens is Y, and the atomic weight is 16.00. So all I got to do is cross multiply and solve, and that'll give me, so if I take 36.9 times Y times 16, that has to equal 63.1 times X times 14.01. Okay, I see my used another marker up. Hey, we're ending the class just in time. I haven't quite run out of markers, but I've gone through a few. All right, now let's do the math and see what we got. We've got 36.9 times 16. That comes out to be 590.4 Y equals 63.1 times 14.01. That comes out to be 884.031 X. Let's divide both through by 590.4. smaller, I'll get 1y equals. I've got this number on the screen, so I'll divide it by 590.4. What I come out with is 1.49734. What I come out with is 1.5x. So I want whole numbers, so I say 2y equals 3x. Multiply by 2. 2 times 1 is 2. 2 times 1.5 is 3. Y is equal to 3. And x is equal to 2. So my formula then, x is 2. It's N2. Y is 3O3. So the correct answer for the compound is N2O3. That's C on the test. Now, what if you panic and you say, oh my goodness, I don't remember how to do that? You can say, oh, but I do know how to figure percentage in a formula. So what I might do and sometimes, sometimes I would do this. Just figure what the percent of nitrogen is in each of the answers. Okay, so for A, I'm going to have 1 nitrogen. So the percent of nitrogen would be 14.01 divided by 14.01 plus the oxygen is 16.00 and multiply by 100. So for the first one, it's 14.01 divided by 14.01 plus 16. And then times 100. That's 46.7%. Okay, that's not the percent nitrogen in the compound. Let's drop down to C, N2O3. What would I get for the percent nitrogen? Well, it would be 2 nitrogens, 2 times 14.01 divided by 2 times 14.01 plus 3 times 16. So 2 times 14.01 is that number divided by the answer, 14.01 times 2 plus 3 times 16, right, times 100. That's 36 that comes out to be 36.858, whatever, 36.9. There's your answer. So if you panic, don't. There's more than one way to work most any problem. So that's what you would do. Okay. All right. Okay, number 24. Let's see if I can. Okay, we want to know the atoms. We want to know the atoms of hydrogen in 12 grams of propane, C3H8, and we're given molecular weight if we need it. So here's what we're going to do. We're going to do a unit conversion. We've got 12 grams of C3H8. we want to go from grams of C3H8 to atoms of hydrogen. All right, molar mass of the compound is given at 44.0. That many grams of compound would be a mole. How many hydrogen atoms would that have in it? Well, it would be 8 moles of hydrogen. So it's 8 times Avogadro's number, 6.02 times 10^23. Okay. I just looked at the answers to see if there's any of them I could eliminate. There's not. Sometimes I know I'm going to get a really big number. So if I've got a power of 10 that's negative, then I know that corresponded to a mistake that is not a possible answer, but I had no such luck. So I take the 12 grams of carbon, I multiply it by 8, I multiply it by 6.02 with an exponent of 23, and I divide it by 44. So 12 times 8 times Avogadro's number divided by 44 is correct. So I'm coming out with 1.313 and a whole bunch of digits times 10^24 power. 1.3 times 10 to the 24th, that's response B on the test. 25. We've got SO2. Okay, here we go. We've got two gases, and the velocity of one divided by the velocity of the second is the square root of molecular weight of one divided by molecular weight of number 2. So now, let's say one is going to be, let's call it SO2. And number 2 is my unknown. So let's set this up. The velocity of SO2, we had 1.23 milliliters diffuse out of that pinhole in 135 seconds. So this will be a velocity in milliliters per second. So I can put that number in up here if I want to. And so I've got 1.25 divided by 135. That's the velocity of the SO2. The velocity of my unknown, it's 1.25 milliliters in 185 seconds. So that's the velocity of the other one. That's going to be the square root of the, oh, somebody didn't catch me. I did a bad thing there. It's an inverse relationship. So I want velocity of 1 and molecular weight of 1 in the denominator, velocity 2 in the denominator, molecular weight of 2 in the numerator. Okay, so number 1 should go down here, and its molecular weight is SO2. It's 32 plus 32 is 64. And this is my molecular weight of my unknown. That's what we're asked to calculate. Okay, now let's do some fraction resolving here, because I don't want to divide them all out and do that stuff. I'm going to write it like this: 1.25 divided by 135, all divided by 1.25 divided by 185. Now, the way you do this is outsides go to the numerator. So it's 1.25 times 185. Insides go to the denominator. 1.35 and 1.25. Now, you can see the 1.25s are going to cancel. So this left-hand side becomes 1.85 no, 185, 185, and 135, like that. And that's going to be the square root of molecular weight divided by 64. So what I'm going to do now is get rid of that radical sign by squaring them. Oh, you need to see my thing. Oh, you're seeing it. Okay. Okay. And I'm going to square both sides.
Can you move your paper up?
I'm sorry.
Never mind.
Okay. I see the time is up. So if any of you have to leave, it's okay. I'm going to hang around and continue until we get this done. And then I'll pause it. I will send an email when I'm back up, ready to go again. But you don't have to come to that one. They will be up on D2L later on today. All right, so I got 135 over 125, 185 over 135. That's going to be equal to M, this is squared, divided by 64. So molecular weight, I'm just going to do this. It's 185 divide by 135. I get that answer. Now I want to square that answer. And I want to multiply it by 64. So what I'm coming out with is 120.186, and some more digits, probably 3 significant figures, yes. That's response B on the exam. So this is a Graham's law problem. It's have to be present. It's an important concept. Okay, now number 26. It says determine the heat of reaction for the combustion of 1 mole of ethylene. So here's what we're going to do. Here's the reaction. It's C2, this is 26, it's C2H4 and 3 O2s, and it's going to 2 CO2s and 2 H2Os. Okay, now, this is my balanced equation. We'll calculate the heat of the reaction. Remember, delta H of reaction is the sum of the delta H of formation of the products minus the sum of the delta H of formation of reactants. These are standard state values. And it gives you in the table, it gives you a table of data on the exam. So let's write out the values and then I'll plug in the numbers. The delta H then for this reaction is the sum of the heats of formation of the products. I've got 2 moles of CO2. So it's 2 times the CO2 value. I'm looking on the table. It's minus 394 is the heat of formation of CO2. I've got 2 waters plus 2. The water values on the table are minus, it is liquid water, and the table only has the liquid present, so I'm okay. It's 2 times 280 minus 286. Now I'm subtracting off the C2H4 value. C2H4 value is plus 52. So everybody see where I got the number? I looked on the table for the CO2 value. It's minus 394, and I had 2 of them. I looked on the table for the liquid water value is minus 286, and I had 2 of them. I'm subtracting off the heats of formation of the reactants, and I subtracted off the C2H4 value. The C2H4 value in the table is plus 52, but I'm subtracting it. Okay, now, there's really 2 ways to go about this one. One way is to look at all of these signs. This number is going to be a negative number. Plus times a minus, this number is going to be a negative number. And minus times a plus, this is going to be a negative number. So one of the things you could do is just eliminate all the signs and put them in the calculator. 2 times 394 plus 2 times 286 minus 52. Plus 52, and then look at whatever your calculator says and change the sign, put a negative sign in front. Sometimes I'll do that. Sometimes I'll look and see, well, a couple of these terms might be negative and some of the others might be positive. I'll group all the negatives together and add them, group all the positives together and add them, and then subtract those answers. The safest, best way really is just to put it in the calculator, what you see right there. So to go 2 times negative 394 plus 2 times negative 286 minus 1 times 52. So 2 times minus 394 plus 2 times minus 286, subtraction minus, not a negative value, minus value is 52. That should give me the correct answer. What I've come out with is minus 1412 kilojoules. These were kilojoules per mole times 2 moles. Kilojoules per mole times 2 moles, kilojoules per mole times 1 mole. Mole units are gone. So there's my answer, and on the exam, that's answer D. Okay. Let's look at number 27. 27 is which of the following electronic transitions for an electron in the hydrogen atom represents the greatest amount of absorbed energy? Now, let's think about what we're doing. Here's a ground state, excited, that's n equal to 1, n equal to 2, n equal to 3, and 4, and 5, and so forth like that. Now, the energy of the hydrogen atom is minus the Rydberg constant. You maybe don't remember it. It's 2.18 times 10 to the 18th. And you divide that by n squared. That gives you these numbers that would go along here. But let's think about something. If I said in the problem, absorbed energy. That means I got to go up. So I'm going from the smaller n values to the larger ones. So if I'm looking at number 1, 1 is going A on, well, let me screen share it with you. That'd be easier. Now, I'm looking at this. In this first one, if I'm going from 1 to 2, that is absorbed energy. But if I'm going 2 to 1, that's emitted energy. I can eliminate C. 8 going to 10, that's going up, that's absorbed. 10 going to 8, that's emitted. So the only 2 responsible answers are 1 or A or B. Now, if I remember, you remember the picture I had over here, the energy levels get closer together as you go up. The biggest gap of the whole bunch by far is the first one, from 1 to 2. So going from 1 to 2 is going to take a lot more energy than going from number 8 to number 10. Now, if you wanted to do the calculation, you could just calculate the change in energy value. It would be final state is 1 over 10 minus 1 over 10 squared minus 1 over 8 squared, or 1 over 2 squared minus 1 over 1 squared. The biggest difference is going to be the 1 to 2. So however you think about it, the correct answer is pretty easy to get. It has to be A, the only one it could be. Okay, we're going to do number 29. How much heat is required to raise the temperature of 4 grams of nickel from 2 to 5 degrees Celsius? So that's just testing to see if you know that calorimeter equation. Q is equal to mass times specific heat times delta T. The mass of the nickel, it's 4 grams. The specific heat of the nickel is given as 0.45 joules per gram per degree C. I want to be sure that this is in grams. Sometimes they give you the specific heat in joules per mole. So double check your units. And now the temperature change, I went from 2 to 5, so it's going to be 5 minus 2 is going to be a 3 right there. Okay, so 4 times 0.45, 4 times 0.45 times 3, the difference. I get 6.4 times 0.45 times 3. I typed it in wrong. I got 5.4 joules. That's response B. So that is okay. And now we probably can do this one pretty straightforward. What's the percent of ionic character in these different substances? So I want the most ionic and the most covalent. And the substances that we have are Pb, Br2, Mg, Cl2, and CO2 and O2. Okay, so now let's look at this and see if we can just reason this out. Oh, I'm sorry, I said O2, it's O3, but it still be the same comparison. Now, if I'm looking at ionic character in a molecule or compound, I'm looking at the difference in electronegativities between the atoms that make it up. And the bigger that difference, the more ionic it is. Smaller that difference, the more covalent it is. So I think I'm seeing a problem with, yeah. Okay, now that makes it a little easier to read. Obviously, these atoms are all the same. So that's going to be the most covalent possible. It's completely covalent. There's a little ionic character to the CO bond because carbon's electronegativity is 2.5 and oxygen is 3.0. So there's a little bit of charge separation, but this one is certainly the most covalent.
Did you see your paper, Dr. Pearson?
Yes. So oxygen is the most, ozone is the most covalent. So it's got to be either answer A or D. Now, so we're looking then at the difference between ionic character of lead bromide and magnesium chloride. Well, on the periodic chart, let's switch over to the camera so you can see periodic chart, we've got magnesium and chlorine, and we've got lead and bromine. Now, the lead is much less electronegative than calcium, and chlorine is much more electronegative than bromine. So calcium chloride is going to be much more ionic than lead bromide would be. The electronegativities between lead and bromine are closer to each other than between magnesium and chlorine by their positions on the periodic chart. So the most covalent one is ozone, and the most ionic one would be magnesium chloride. And that's what we get if you look at this screen share. So the correct answer is D. To predict the bond angles around carbon in, this is ethylene, is the name of the compound, but it's H2CCH2, that's the way it's written. By implications, these hydrogens belong to that carbon, and these hydrogens to that carbon, and these carbons are connected together. So let's go ahead and do that part. I've got 2 hydrogens in carbon, and I've got 2 hydrogens. Now, I can't do the math thing on this. And carbon, what does it have? Does it ever have lone pairs? No. So it has to have a double bond right there. So that is the Lewis bond or valence bond structure for ethylene is going to look like that. Now, if I want the shape of the molecule, let's skip off of there so you can go back over here. Here's what the molecule has to look like. It's got 2 hydrogens on that carbon, 2 hydrogens on that carbon, and these 2 carbons are together like that. When I put the hydrogens on, each hydrogen has 1 bond as it's supposed to. Both carbons, each one of them has to have 4 bonds. We had 1, 2, we have to have a double bond here to make that work. So that's what the structure looks like. Now, if you want to pick any one of the atoms in there, we want a bond angle between around all of the carbons. So let's focus our attention on that carbon. The other one will be the same. Now, what is its VSEPR notation? Well, it would be A, and then how many atoms does it have attached to it? 1, 2, 3. It's AX3. How many lone pairs? None. So what is the shape of AX3? It's trigonoplanar. So this carbon atom is going to have, say, put the hydrogens here and here and a double bond there. The bond angles are 120 degrees. All of them are 120 degrees. The other end looks the same. So the correct answer for number 30 would have to be C. Okay. All right. So that completes everything. Now I'm going to actually stop the recording. Well, I'll first pause it so we'll have a chance to talk a little bit if we want to. Close this down. No, I want to put it down, not close it. And I want to go back to no, I don't want to do screen sharing at all. Okay, yeah, you're seeing what I want you to see. Okay, all right, let's go here and do pause recording.